Hello and welcome to today's video. Today we're going to be learning about something called calorimetry, which is a very important aspect of thermodynamics. It allows us to find out the change in enthalpy. As you recall before, we've mentioned that enthalpy cannot be measured directly, so we have to have some indirect means of finding it. And the easiest way is the change in enthalpy. And calorimetry is one of the ways that allows us to do that. Calorimetry literally is just the measurement of heat flow into or out of a system. And we use a calorimeter to find that. Calorimeters are great because you can control lots of different variables as you are measuring this change in heat. But before we can jump right into discussing all the stuff about calorimetry, we need to know some kind of key terms that come into play with this. And one of those is the heat capacity. Heat capacity is the amount of heat that's needed to raise a substance's temperature by 1 Kelvin or 1 degree Celsius. Now, it doesn't really matter Kelvin or Celsius in this sense, because if you go up 1 Kelvin or if you go up 1 Celsius, the net change in temperature is still the same. They go up by scales of 1, which is very convenient. So, one of the things that affects heat capacity is not only just the substance itself, but how much of that substance do you have. So in case in point, if you have a swimming pool versus a fish tank takes considerably less heat to heat up and change its temperature than a swimming pool does, because of the sheer volume and mass of water that's available to you. So different substances require different heats to raise their temperatures, and different amounts of substances affects the amount of heat that's required to change their substances. Heat. Beyond heat capacity, we also have what's known as molar heat capacity. And molar heat capacity is a little bit more useful because now we're being specific to saying that if you have 1 mole of a substance, how much do you need to raise that temperature? Whereas heat capacity is kind of a more generic term of it. This is getting now to you actually have a mole, which is useful. So where heat capacity is just like a general broad term, molar heat capacity is if you have exactly a mole of that substance. Specific heat capacity, which is used more often for calorimetry, is when you have only 1 gram of that substance. It's also sometimes just referred to as the specific heat. And the variable for it is just the little lowercase c, which is going to be something we're going to be using a lot through the rest of this particular lesson. So how do we find the specific heat? Well, there's a very simple equation that works with it, and it's the amount of heat transferred, measured in joules, divided by the mass in grams of the object or substance, times its change in temperature, either Kelvin or degree Celsius. So if we look at it in terms of variable, Q, remember, is what we use for heat, M is for mass, and delta T is for T. And what you end up with for units is joules per gram Kelvin, or joules per gram degree Celsius. But you have to remember that a change in temperature for Kelvin is equal to a change in temperature in Celsius, so it's either way they can be used pretty much interchangeably for us. So here's a quick example. Imagine you have 50 grams of water, and you change its temperature 1 Kelvin. So you only got 1 tick up in terms of temperature change. The amount of heat required to do that is 209 joules. If you plug it into our equation, you end up with a heat capacity of 4.18 joules per gram Kelvin. Now, since you have no reference for this, I'm going to tell you that that is a very, very, very high heat capacity, which is why water can absorb lots of energy before it changes temperature, which is good for us, because imagine if it had a really low specific heat capacity and the temperature changed, you're mostly water. If the specific heat capacity of water was really low, not much energy would need to change, and your body temperature would rise really fast, and that would be definitely not a good situation for you. Conversely, if you look at the heat capacity of aluminum, that only has a heat capacity of 0.9 joules per gram Kelvin. So the amount of energy needed to raise the temperature of aluminum is significantly less than the amount of energy needed to raise the temperature in terms of water. But that isn't good if you're trying to find just the specific heat of something. Most of the time, as we discussed at the beginning of this video, is we're not wanting to find specific heat. We're usually looking for what is the change in H. What is that change in enthalpy? Well, we can find that by using magical algebra. I know it's been a while since some of you just used straight algebra, but if you just rearrange the variables a little bit, you end up with Q equals mc delta T. So now, if we know the mass, the specific heat, and the change in temperature, we can figure out how much heat energy is actually moving back and forth between the two, which is usually what we're actually looking for. Because you can measure the mass, you can measure the temperature change, and you can just look the specific heat capacity up. A lot of those are in huge volumes of books. And then you can use that to find how much heat was actually transferred. So there's a couple different ways we can find this delta H, which is equal to Q. One of the most common ones is in a constant pressure calorimeter, which, just as its name applies, the pressure is held constant within the calorimeter. It's not allowed to change. It allows you for a direct measurement of the delta H. So what you can say, since it's a direct relationship, is that delta H, or the change in enthalpy, is equal to Q, and they put this little sub P, which just means heat transferred under constant pressure. So it's that Q we had in that Q equals mc delta T. So what you can say is that the change in enthalpy, the delta H, is equal to the Q that you can calculate through using MC delta T. Typically we do this within a solution, just because solutions are great at transferring heat back and forth. And the most common one is water. So we have to have a couple of assumptions to go along with this. One, we're assuming that pressure is constant, okay? Which is easy enough to do in most situations, but we're assuming that pressure is not changing. We're also assuming that the calorimeter prevents any gain or loss of heat from the solution to the surroundings. In other words, we're assuming that the only heat transfers between the substance that's in the solution and the solution itself. So not the air, not the calorimeter itself, and so forth. The other thing we're assuming is that all of the heat that's lost or gained by the solution, whether or not the water heats up or cools down, is only due to the reaction that's taking place or due to the heated object that's inside there and not to anything else. So if you have an exothermic reaction that's taking place, you have a negative QRxN, or negative heat of the reaction, is equal to positive heat of the solution, because the reaction is losing the heat, the solution is gaining the heat. Endothermic, on the other hand, is just the opposite. You're absorbing the heat from the solution, so it's a negative Q for the solution, and it's a positive Q for the reaction as it pulls in that heat. This is an example of a calorimeter here. We'll talk a lot more about this in class as we use them in a couple of actual lab experiments. So what do you get to do? Well, we're going to use styrofoam cups. They're open to the surroundings, which means the pressure is relatively constant because it's just atmospheric pressure. Since the cup is insulated, the heat is not transferred easily to the surroundings. And we're going to determine Q, which therefore equals our delta H, by looking at the change in temperature within the system, or the calorimeter. Now we're making a couple of assumptions here. Now we're assuming that some of the heat will get lost if you leave it sit there long enough. So if we take fast enough measurements though, we can get a pretty good gauge of what our delta H is going to be. And just because robots are freaking amazing, here's some dude who draws all this artwork on styrofoam cups, and I found him, and why wouldn't you have a robot attacking a city? Or a very, very pretty wave, or looks like a little cherry blossom tree there. Art's awesome, especially since I can't do it. Another type of calorimeter that we can use is something called a constant volume calorimeter, in which the volume is kept constant, but the pressure can be allowed to change. Usually this is used to undergo something that's going through complete combustion, because now your pressure is going to change as the reaction takes place, but your volume will stay the same. So we usually have this take place in a sealed container filled with a set volume of water, and the change in temperature of the water is then used to calculate the heat transfer from the reaction. So the basic idea is still the same between the calorimeter, or the volume calorimeter, which is what we call constant volumes, and the other type, but the main difference is just that you're in a sealed container, we're dealing with things that are more heated up. The one thing with bomb calorimeters is you have to know the specific heat of the calorimeter to be able to use it. So we get this thing called the big C cal, which is the specific heat of the calorimeter. So you have to change the formula a little bit. So the Q of the reaction now is equal to negative C cal times delta T. And that's because you have to account for the fact that the calorimeter itself is going to be allowed to absorb some of that heat energy, and you have to account for that with the specific heat. Okay, so hopefully all that kind of makes sense. We'll talk more about it a lot in class. We'll do some practice calculations. We'll have a lot of fun with it. You're going to love it. I guarantee it. All right, so maybe the guarantee thing was a little weird. And if you're still watching this, that's also a little weird, because we're kind of done with notes now. So you can probably put your pens down. Don't really need to pay attention anymore. Not going to do anything funny. Have a good night.